AI feels like large language models and image generators, doesn't it? That's kind of the main story
Yeah,
today.
that's what grabs the headlines.
But if you dig deeper,
Yeah.
what are the fundamental ideas, the bedrock this whole field is actually built on?
Right. Because the current AI boom, it's not really an overnight thing. It rests on decades of foundational
This
research.
that came way before deep learning was everywhere.
Exactly. Concepts developed long ago. And those ideas, well, they often get missed in all the noise.
So let's try and cut through that noise today. We're taking a deep dive, not into the latest, viral AI tool, but into a source that really lays bare those essential foundations.
Yeah, something that shows you the vast landscape of AI beyond just the headlines.
And our source material for this, it's specific. We're looking at key excerpts from a really important textbook, AI Foundations of Computational Agents, 3rd edition.
Yeah, that's the one.
So our mission today is pretty clear. We're going to unpack this book. We'll figure out who it's really for, try to grasp its central message,
Highlight some fascinating bits from the chapters.
and definitely pull out some surprising insights you might not find elsewhere. It's sort of like your shortcut to being truly well-informed about AI's breadth, right?
Exactly. A way to get the bigger picture.
Okay, so let's start there. Who is this book actually aimed at? The reviews give us pretty good clue, I think.
They do. Yoav Shoam, for instance, calls it appealing to a broad audience,
Mm,
which is interesting.
broad, okay. But he also specifically mentions people relatively new to the field for whom AI and deep learning appear almost synonymous. That feels really key.
It is key because the authors, they make a point of harmonizing recent developments, such as generative AI, with more traditional methods
Ah, so they're bridging the gap.
within a unified agent framework.
Yeah.
Yeah, exactly. Bridging the gap.
Okay, so let's say your view of AI pretty much starts and stops with things like ChatGPT or maybe Midjourney.
Then this book is kind of designed for you.
Right. To broaden that view, it gives you a comprehensive look at many different AI topics, explains the intuition behind some complex ideas.
And crucially, shows how all this modern AI stuff fits into this larger, more established framework. It gives context.
So it helps you see the whole forest, not just like the trendy trees.
That's a good way to put it. You become genuinely well-informed across the whole AI spectrum, not just the latest buzzwords.
So what's the central idea then? The thing tying it all together, the book's core theme?
Well, the book frames pretty much all of AI through this lens of computational agents.
Agents. Okay, what does that actually mean? Is it like robots walking around?
Huh, not necessarily. Less sci-fi, more
Mm,
fundamental. An agent is simply something that acts in an environment,
okay.
and it makes decisions based on a really specific set of inputs. Its prior knowledge, any stimuli it perceives, its past experiences, what its goals or preferences are, and, its abilities, physical or computational.
So it doesn't just know things. It doesn't have access to everything.
Absolutely not. The book's view, which they show in Figure 1.4, is that an agent only acts based on that specific set of inputs. That's its entire window on the world.
Wow.
And that view applies to everything from a simple thermostat deciding when to click on, all the way up to, say, human society viewed abstractly. It's a surprisingly powerful and encompassing model.
And the book provides the methods, the building blocks for creating these agents,
Exactly. It gives you the foundational methods for building intelligent agents.
covering a whole range of stuff.
Oh, yeah, a wide spectrum. From how an agent might represent what it knows, how it reasons logically, how it handles uncertainty, plans its actions, or learns from data.
And it connects the old and new.
Yes. It connects traditional AI techniques, things like logic and search, with modern ones, including, recent generative AI advancements. But it's all viewed through that agent lens. That's the unifying theme.
Okay, that makes sense. Let's dive into some highlights from the chapters then, see how this agent idea plays out in different areas. Chapter 1 kind of sets the historical stage, right?
It does. It starts by noting something interesting, that humans have always used technology to model themselves. Think clockwork, hydraulics, and now computers.
And get this, some of the very first programs written for those early computers were actually AI programs. That historical context often gets lost, I think.
It really does. Think about it. Samuel's checkers program. It beat a state champion way back in 1961.
Wow.
And Wang's program proved hundreds of logic theorems from Principia Mathematica. Newell and Simon's logic theorists discovered proofs. Early AI was fundamentally about logic, about search, about structured thinking.
Not just calculation.
No. And parallel to that, you had the early work on neural networks, McCulloch and Pitts, Minsky, Rosenblatt.
Right, that track had its ups and downs.
It did. Minsky and Paper's critique was a big setback, but the foundational work continued through the 80s and 90s.
And then things really took off later.
Yeah, with breakthroughs like ImageNet, Krzyzewski's work, and then more recently major advances like GANs by Goodfellow and Transformers by Vaswani and others. Now neural nets are pretty dominant for perceptual data and generative AI.
But the agent framework still applies across all of this history.
Yes. Whether it's that thermostat or a complex trading system, the book talks about the agent design space dimensions, like how it represents the world, its computational limits. Is it perfectly rational or bounded? Does it learn? How does it handle uncertainty? What are its preferences, and so on? Figure 1.8 lays this out.
The book gives examples too, right? Like a trading agent.
Yeah, a trading agent interacting with an information environment, monitoring prices, maybe doing proxy bidding, buying multiple items.
Or even a smart home.
Right, a smart home acting as a diagnostician if something breaks, or maybe even a tutoring agent teaching you how your fancy new appliance works, adapting to what you already know.
There's an interesting point in Chapter 1, almost philosophical. AI representations often specify what needs to be computed, not the step-by-step how.
That's a really key difference from traditional programming, isn't it? The AI agent, using its reasoning processes, figures out the how itself, often by searching through a space of possibilities.
And they don't always need the absolute perfect answer either.
No, exactly. The book introduces satisficing solutions, basically. Good enough according to some description of what's adequate, or approximately optimal ones, close enough to the best possible. Perfection isn't always the goal, or even feasible.
Okay, so Chapter 3 then dives into how agents find these solutions, particularly through searching.
Right. Planning is often framed as pathfinding in a state space graph.
Like finding your way on a map.
Exactly. Nodes are states, like locations, and arcs are actions, like moving between locations. A plan is just a path from your start state to your goal state.
Like that delivery robot example, finding a path between buildings.
Or a video game character where the state isn't just position, but maybe includes fuel level or coins collected. Or even a simplified tutoring agent where the state is the set of topics the student knows or has been introduced to.
The book covers standard search algorithms.
Yes, things like breadth first, depth first search. And it specifically mentions a search and the conditions needed for its admissibility proof, basically. Guarantees it finds the shortest path under certain conditions, like positive action costs, and using an optimistic heuristic estimate.
And searching using abstractions.
Yeah, searching in a hierarchy of abstractions to make the problem more manageable.
Okay, moving on. Chapter 4 tackles reasoning with constraints. This sounds like a scheduling problem.
Exactly. Or configuring a complex product. You have variables who attends which meeting when, which component connects to what, and constraints person A can't be in two places at once. Component X only works with component Y.
These are called constraint satisfaction problems, or CSPs.
Right. And the book shows how you can solve these by searching, often using depth-first search, but pruning branches that violate constraints.
Making the search smarter.
Definitely. It also talks about consistency algorithms like generalized arc consistency, GAC. These simplify the problem before you even start searching by removing values that clearly can't be part of any solution.
What if you can't easily prune or simplify?
Then you might use local search. You start with a complete assignment, even if it violates some constraints, and you iteratively tweak it, trying to reduce the number of violations. Things like random restarts help avoid getting stuck in bad spots.
And population-based methods, like genetic algorithms.
Yeah, those maintain a whole population of potential solutions and evolve them over time. Beam search is another one mentioned.
The chapter also brings up soft constraints, right? Not just hard yes-no rules.
Right. Soft constraints have a cost associated with violating them, whereas hard constraints have, effectively, infinite cost. And it connects this to optimization methods like gradient descent, noting its importance, especially in deep learning, for minimizing cost functions.
Makes sense. Then Chapter 5 jumps into logic, specifically propositional logic.
Back to basics, in a way. Statements that are either true or false. You build a knowledge base, a KB of facts and rules.
And then you ask it questions like, is light L1 on? The book explains logical consequence. Does the KB guarantee the answer is true?
It also links this back to constraints, showing how you can represent constraints using logic and use efficient SAT solvers, which are specialized constraint solvers for logic problems.
They define definite clauses to simple rules and facts.
Yeah, like if switch 1 is on ND bulb 1 is okay, then light 1 is lit. Facts are just clauses with no if part. The book has examples of querying a KB made of these.
And debugging these KBs if they give wrong answers.
Right, knowledge level debugging. searching the proof space to find missing rules or incorrect facts. It also covers negation as failure, basically, assuming something is false if you can't actively prove it's true, which is how we often reason informally.
And causal models come up here too.
Yes, defining not just correlation, but how one thing causes another. Example 5.34 uses an electrical circuit to show how you can use such a model to predict what happens if you intervene, if you actively flip a switch, for example.
That's a big distinction.
Huge. The summary highlights abduction, finding explanations, diagnosis, a type of abduction, and how causal models predict intervention effects. SAT solvers are noted as really important tools.
Okay, let's shift gears into the area people probably associate most with modern AI machine learning, starting with Chapter 7 on supervised learning.
Right, this falls under the book section on learning and reasoning with uncertainty. Supervised learning is about learning a function from labeled data. You give it input-output examples.
And it learns to predict the output for new inputs.
Exactly. The book talks about measuring the error using loss functions. Different tasks need different ways to measure how far off the prediction is, like 0-1 loss for just getting it right or wrong,
Oh.
or squared loss for numerical predictions.
And the best prediction strategy depends on that loss function.
Yep. Predicting the mode, median, or mean might be optimal depending on how you measure error. Precision and recall are also key metrics, especially for classification.
It covers basic models like decision trees.
Yes, they're presented as a foundational interpretable model, like a flowchart of if-then-else questions about the input features.
And how to avoid overfitting, learning the training data too well.
Right. Using a separate validation set to tune hyperparameters, like the complexity of the tree, and watching the validation error. Stopping training early if validation error starts increasing is a common trick.
Gradient-boosted trees are mentioned as a more powerful approach.
Yeah, building an ensemble model by sequentially adding decision trees that correct the errors of the previous ones.
Okay, then Chapter 8 is the big one, neural networks and deep learning.
This is where representation learning really shines, learning useful features directly from the data using multi-layer networks.
Artificial neurons, or units. The book points out the incredible scale of modern networks parameters in the hundreds of billions, maybe 10, 11.
Which sounds huge, almost like the number of neurons in a human brain.
But then it makes a crucial comparison. A tiny worm, C. elegans, has only 302 neurons.
Yet it exhibits complex, integrated behavior that our current artificial units, even billions of them, can't replicate. It's a humbling reminder that our artificial units are vastly simpler than biological neurons.
So these networks are feed-forward layers of functions composed together. Activation functions like RILE-U and softmax add necessary nonlinearity.
And learning the parameters, the weights and biases, is done using backpropagation, which, under the hood, is basically implementing stochastic gradient descent to minimize the loss function.
They talk about improving generalization here too. First, make sure it can fit the training data, then tackle overfitting. Monitoring that training versus validation error curve is key.
Convolutional neural networks, CNNs, get covered great for grid-like data-like images, using shared filters or kernels applied to local patches.
And then models for sequences, like text or time series.
Recurrent neural networks, RNNs, come in there. They have a hidden state that carries information from previous inputs to influence the processing of the current input.
But RNNs have issues with long sequences, right?
They can, particularly with vanishing or exploding gradients. LSTMs, long short-term memory networks, were developed to address this, using special gating mechanisms, input, output, forget gates to control the flow of information and gradients more effectively.
And then the really big recent development, attention and transformers.
Right. How do you process a long sentence and understand, say, pronoun references or word meaning in context? Attention mechanisms allow the model to dynamically weigh the importance of different parts of the input sequence when processing any given part.
Like focusing on relevant words.
Exactly. Using a probability distribution over other words in a window. The example given is, the bank is on the riverbank. Attention helps the transformer figure out which meaning of bank applies based on the surrounding context. River. Positional encoding is also added to keep track of word order.
And large language models, LLMs, are presented as a type of transformer architecture.
Yes. The chapter also briefly touches on other architectures, like autoencoders for dimensionality reduction, generative adversarial networks, GNNs, and diffusion models, which are important for image generation.
Okay, Chapter 9 shifts back to reasoning with uncertainty, but using probability theory.
This is crucial for agents operating in noisy, unpredictable worlds.
Mm-hmm.
Bayes' rule is absolutely fundamental here. How do you update your belief in a hypothesis or model, given some new evidence? PM. PMES, ESM. PS.
Likelihood times prior divided by evidence probability.
Exactly. Inference calculating these probabilities can be exact or approximate. Often the models are too complex for exact calculation.
Belief networks are a key tool here.
Yes, also known as Bayesian networks. They use directed acyclic graphs, DTs, to represent variables and their conditional dependencies. It's a compact way to represent complex joint probability distributions by exploiting conditional independence. Great for things like diagnosis.
How do you build them?
Identify relevant variables, draw arcs representing direct causal or influential relationships, and then specify the conditional probability distributions, CPDs, for each variable given its parents in the graph.
They mention using decision trees to represent these CPDs sometimes.
Yeah, especially when there's context-specific independence where a variable only depends on a parent under certain conditions. It makes the representation more compact. Things like noisy or models and logistic regression are also mentioned as ways to define CPDs.
And inference in these networks, finding probabilities.
Often involves summing out variables from the joint distribution represented by the network. Variable elimination is a key exact inference algorithm, a form of dynamic programming.
Temporal models also come up?
Yes, models dealing with sequences over time. Hidden Markov models,
Wow.
HMMs, are a classic example. The state depends only on the previous state, and observations depend only on the current state. Dynamic belief networks generalize this,
And learning the probabilities in these models from data.
often using maximum likelihood estimation, MLE, or maximum a posteriori MAP estimation, updating counts based on observed data.
There's an example of a help system learning which page is correct based on user feedback.
Right. Updating probabilities based on experience, then using these models for filtering, estimating current state from past observations, or prediction, estimating future states. Sampling methods like particle filtering and MCMC methods like Gibbs sampling are mentioned for approximate inference when exact methods are intractable.
Okay, quick detour into Chapter 10. Unsupervised learning.
Learning from data where you don't have target labels. Finding inherent structure.
Like clustering.
Exactly. Partitioning data points into groups based on similarity. K-means is a classic algorithm for this, trying to minimize the square distance between points and the center of their assigned cluster. It's iterative.
And expectation maximization, EM.
That's used when you have latent or hidden variables influencing your data. It alternates between estimating the expected values of the hidden variables, E step, and then updating the model parameters based on those estimates, M step.
Got it. Now, Chapter 11 circles back to causality. This seems important.
Hugely important. Inferring cause and effect, which is distinct from just seeing correlation. The key concept introduced is the intervention, denoted do XX. It means actively setting a variable x to a value x rather than just observing it.
Like in a drug trial.
Precisely. Example 11.5 used a drug trial where sickness causes people to drop out. This messes up simple correlations. Observing P outcome drug was taken is different from P outcome we administered the drug, i.e. P outcome to drug. The latter requires controlling for confounders.
And the book stresses you can't get causal conclusions from just observation.
Without making assumptions about the underlying causal mechanisms. Even randomized controlled trials rely on assumptions about the randomization working properly. Inferring the effect of interventions is the goal, and it's harder than just finding correlations. You can sometimes infer causality from observation, but only with explicit causal assumptions.
Okay, Chapter 12 combines planning with this uncertainty. Planning with uncertainty.
Right. Decision networks are introduced here. They extend belief networks by adding decision nodes, choices the agent makes, and utility nodes, representing the value or desirability of outcomes.
So how do agents represent what they value? Utility theory.
That's the standard normative approach. But the book brings in prospect theory, which is fascinating. Utility theory says how a rational agent should value outcomes. Prospect theory describes how humans actually make decisions.
And we're not perfectly rational, are we?
Not according to prospect theory. We don't perceive absolute values. Our preferences are based on the difference from our current situation or a reference point, like how water feels hot or cold depending on what your hand was in before, or visual illusions like Miller-Lire. It explains seemingly irrational choices.
How do you solve these decision problems?
For sequential decisions under uncertainty, techniques like backward induction, starting from the end and working back, or applying variable elimination to the decision network over time can find the optimal policy.
The umbrella example sounds interesting.
Yeah, example 12.18. It shows a case where getting a weather forecast might be useless if, regardless of the forecast, the optimal action, like taking an umbrella, doesn't change because the potential cost of getting wet outweighs the inconvenience. Partially observable decision processes, POMDPs, are mentioned for when the agent doesn't even fully know its current state.
Then Chapter 13 gets to reinforcement learning, RL, learning by doing.
Exactly. Learning what actions to take in an environment to maximize a cumulative reward signal purely through experience. Trial and error.
Temporal difference, TD learning is key.
Yes, learning from sequences of state, action, reward, next state, SARS. Updating value estimates based on the difference between predicted and actual outcomes. Q-learning is a very popular TD algorithm. It learns the optimal Q function, which represents the expected future reward of taking action A in state's ends and then following the optimal policy thereafter.
The core challenge in RL is often exploration versus exploitation, right?
Definitely. Do you stick with what you know works, exploit, or try something new that might be better, explore? Upper confidence-bound UCB methods are mentioned as a way to guide exploration by explicitly modeling the uncertainty in the Q value estimates. You prefer actions with high estimated value and high uncertainty. And SARSA is another algorithm mentioned. How's it different from Q-learning? SARSA stands for State Action Reward State Action. The key difference is that Q-learning learns the value of the optimal policy directly, while SARSA learns the value of the policy the agent is currently following, including its exploration steps.
So SARSA might be more conservative.
It can be. Because its Q values depend on the current exploration policy, it might learn to avoid states that are risky to explore, even if they are part of the theoretically optimal path. The example given is a robot near stairs. Q-learning might learn the optimal path that goes near the edge, while SARSA might learn a safer path further away because falling during exploration is costly.
Interesting nuance. Okay, Chapter 14, multi-agent systems.
Now we have multiple agents interacting in the same environment, often with different, possibly conflicting goals.
Game theory territory.
Exactly. Minimax alpha beta search is covered for two-player, zero-sum games like chess or Go. Finding the best move, assuming your opponent plays optimally to minimize your score.
What about games where players move simultaneously or don't have perfect information?
Then the concept of Nash equilibrium becomes central, a state where no single agent can improve their outcome by unilaterally changing their strategy, assuming others keep theirs fixed.
Like a stable point in the game.
Sort of. Example 14.2 uses a simple sharing game to show there can be multiple Nash equilibria, and how things like bribes can change the outcome. Eliminating dominated strategies is one way to find these equilibria. The soccer penalty kick example, 14.9, illustrates how thinking can cycle in simultaneous move games.
Can RL be used here?
Yes, but it often requires learning stochastic probabilistic policies, especially if there are multiple equilibria or imperfect information. Agents might not even know the exact outcomes or other agents' utility functions.
Chapter 15 goes deeper into representation with individuals and relations, beyond simple true-false.
This is first-order logic, or predicate calculus. Now you can talk about specific individuals, like block A. Their properties is right or block A and relations between them. Building logical models of the world.
Right. Mapping real-world individuals to constant symbols in the logic and relationships to predicate symbols. Example 15.10 shows mapping an electrical domain, like figure 5.2, into logical facts and rules.
How does reasoning work here? Often involves finding ground atomic consequences, basic facts implied by the KB. Techniques like substitution and unification, find the most general unifier, MGU, are used to match patterns and rules. A bottom-up proof procedure is sketched. Figure 15.7, note source error mentioned, figure 15.8.
Function symbols are also introduced.
Yes, to refer to individuals indirectly, based on their components or structure, like representing dates, times, or lists.
And applications in natural language processing.
Using logic, specifically definite clauses, to represent grammar rules, context-free grammars, and semantics. Building systems that can parse an English sentence into a logical query for a database. The book contrasts this traditional approach with modern LLMs.
Equality is mentioned as a special case.
Yeah, asserting that two different terms or descriptions actually denote the same individual. Like chair 1 and the chair B, the window, might be the same object. This requires special handling and inference. It's not just a simple predicate.
Chapter 16 then talks about ontologies, formal knowledge representation.
It's about structuring knowledge, about classes of things and their properties, defining concepts formally.
Like defining a national sports team.
Exactly. Example 16.11 uses genus, sports team, and differentia, represents a nation, to define it precisely. Ontologies consist of individuals, classes, properties relating them, and axioms that state restrictions and relationships. Example, every manager is an employee. The key advice given is practical. Reuse existing ontologies whenever possible for knowledge sharing. Don't reinvent the wheel.
Makes sense. Chapter 17, Relational Learning. Learning from data with individuals and relations.
Learning patterns directly from the structured relational data.
Collaborative filtering is given as an example.
Yes, predicting user preferences, like movie ratings, based on the preferences of similar users and properties of items. This often involves learning vector representations or embeddings for users and items in a way that captures their relationships.
More complex techniques are mentioned too.
Like polyadic decomposition with inverses, designed to learn embeddings for relations themselves, handling more complex relational structures.
Okay, nearing the end. Chapter 18 looks at applications and societal impacts. This feels very relevant today.
Extremely. It covers explainable AI, XAI, discussing concepts like transparency, interpretability, explainability, fairness, safety, accountability, trustworthiness.
These terms overlap a lot.
They do. And the book notes they can sometimes be in tension. Like, a highly complex black box model might be very accurate but not interpretable, while a simple, transparent model might be easier to understand but less powerful. Causal models might help provide better explanations.
Transportation comes up, autonomous vehicles.
Yes, using many AI techniques.
Mm-hmm.
Positioning, planning, including ethical choices and preferences, scheduling. Highlighting potential benefits like safety and traffic flow. AI for social good and sustainability is also discussed.
Linking AI to the UN Sustainable Development Goals.
Right. How multi-agent systems might help manage public health resources or avoid tragedy of the common scenarios.
And AI regulation.
Increasingly critical. The book mentions frameworks like the OECD AI principles, the EU AI Act with its risk-based approach, banning certain uses like social scoring and placing requirements on high-risk systems, and the U.S. blueprint for an AI Bill of Rights. Liability issues are also touched upon.
Finally, Chapter 19, Deploying and Maintaining AI, Practical Considerations.
Like choosing the right AI technology, Figure 19.1 provides a decision tree based on factors like the stakes involved, data availability, abundant versus scarce, homogeneous versus heterogeneous, and the amount of expert knowledge available.
And it comes back to a really tricky point, preference elicitation.
Yes. How do you figure out what the AI should actually value or prefer, especially when the stakes are high?
This isn't something you can just learn from data.
Generally not, the book argues. Preferences often need to be explicitly specified. Inverse reinforcement learning tries to infer preferences from observed behavior, but it's very challenging. And what do you do when different stakeholders have conflicting preferences? Combining them is a major unsolved problem.
Wow. Okay, that was a whirlwind tour through the sheer breadth of concepts in this book. It really drives home how much more there is to AI than just, training the latest model.
It absolutely does. It shows AI has these deep roots, diverse branches, all contributing to this core idea of building intelligent agents.
So let's pull out some of those moments that really stood out, the surprising, fascinating, maybe even awe-inspiring insights from digging into this material.
Okay, insight number one for me was definitely the ancient ambition of AI. The idea that humans didn't just start thinking about artificial minds with silicon chips. The book points out we've used technology, clockwork, hydraulics to model ourselves for centuries.
And then the realization that some of the very first computer programs were AI programs, proving logic theorems, playing championship-level checkers in 1961. AI wasn't an add-on. It was there from the start. It wasn't about speed first. It was about thought.
Exactly. Insight number two, the agent's limited window. That simple model from Figure 1.4, an agent only acts based on prior knowledge, stimuli, past experience, goals, and abilities.
That's really it. No magic.
Nope. It has no access to anything else. Applying that stark, constrained view to everything from a thermostat to society. It's a really powerful framing device. Makes you think about what intelligence even is.
Insight 3. AI solving the what, not the how. That feels like a fundamental shift.
It is. Instead of writing step-by-step instructions, you specify the goal, the desired state, the what. The AI's task becomes figuring out the complex path or method, the how often, through search or reasoning. It's the different level of problem solving.
Insight 4. Good enough is often the goal. We tend to think AI needs perfection.
But the book's emphasis on satisficing or approximately optimal solutions is so practical. Real-world problems rarely need or allow for the absolute best solution. Effective AI is often about being adequate, not perfect.
Insight 5. The scale comparison, huge networks versus the tiny worm. Modern ANNs have maybe 100 billion parameters, nearing brain neuron counts.
Yet C. elegans, that millimeter-long worm with just 302 neurons, shows integrated behaviors are massive, yet simple artificial units can't touch. It's incredibly humbling and forces you to question our definitions of complexity and intelligence.
Insight 6. Understanding context, like the word bank. It's not just about dictionary definitions.
Right. The way attention mechanisms and transformers learn to weigh which other words are relevant to understand a specific word's meaning in context, it's like the model is learning to selectively listen. That's fascinating.
Insight 7. Causality requires assumptions. You can't just get it from looking at data.
That point about needing assumptions, even for randomized trials, to draw causal conclusions from observational data is so critical. P-outcome do is fundamentally different from P-outcome drug. AI systems need to grapple with this.
Insight 8. Humans aren't utility maximizers. Prospect theory shows how we really decide.
Yeah, moving from the normative, how we should decide if rational, to the descriptives, how we do decide. Our choices being relative to a reference point, not absolute outcomes that explains so much about human irrationality and is crucial for AI interacting with us.
Insight 9. RL isn't just about the best path, but sometimes the safest path to learn.
The SARSA algorithm learning based on the current exploration policy. It might avoid a theoretically optimal path if exploring it is too risky. It incorporates the cost of learning itself into the policy. That's a subtle but important difference from pure optimality.
And Insight 10. Building logical models isn't just translation, it's conceptual engineering.
Deciding what counts as an individual, how to represent relations, how to handle equality, is this the same chair? These aren't just technical details, they are deep choices about how you carve up the world to represent it logically.
These insights definitely paint a much richer, more nuanced picture of AI, its history, its challenges, the sheer diversity of approaches.
It really underscores that AI is so much more than just optimizing parameters in giant neural networks.
So wrapping up this deep dive, we've journeyed through AI foundations of computational agents, figured out who might find it useful, explored its agent-centric viewpoint, touched on key areas from logic and constraints to deep learning and multi-agent interactions, and surfaced some really thought-provoking ideas.
Yeah, the book makes it crystal clear. AI is this rich, multidisciplinary field with a serious history. Understanding these foundations, well, it seems essential for really grasping the full scope of AI today and thinking about where it might head next.
And as a final thought, something to chew on, drawing from that discussion in Chapter 19 about deploying AI, especially for high-stakes decisions, the book highlights this huge challenge of preference elicitation, figuring out what the AI should actually aim for.
Right. It argues preferences aren't generally learnable from data alone. People often disagree on values, and there's no easy way to combine conflicting preferences.
So here's the provocation. If we find it so incredibly difficult to define, measure, and agree upon human values, how can we ever build AI systems that truly and reliably reflect those values, particularly when the consequences are significant?
It's a massive question for the future of AI.
And one this book really pushes you to think about. We hope this deep dive has broadened your perspective on artificial intelligence.